Okay, this video is going to cover the first half of this chapter 8-9 review, the first 2 pages. Question 1 here comes from section 8.1, studying parabolas. We discussed 2 types of parabolas in 8.1. One type is a parabola that is vertical parabola, opens up or down. Okay, so why there's something like this, or it could be flipped upside down, something like that. The second type of parabola discussed was the horizontal parabola, opening either to the left, like that, or to the right, or to the left, something like that. We've got to decide which type of parabola this is, and the way that was discussed in class is you look at the variable that's being squared. In chapter 4, when we were studying functions, it was the x variable that was always being squared, which always produced a vertical parabola, opening up or opening down. Since the y variable is being squared, this is going to be the type of parabola that opens horizontally, or either to the right or to the left. Now, in section 8.1, horizontal parabolas are of the form y squared equals 4px. What we did is we compared the equation given to us to this general form. So what we need to do in this one is manipulate it so that y squared is on the left side. The -8 needs to be on the side with the x. So if we divide both sides by -8, we're going to get the equation y squared equals -1/8 times x. Now when we compare this to the general form of the equation and equate coefficients, 4p is the coefficient in front of x and -1/8 is the coefficient in front of x. We set these equal to each other to solve for p. 4p equals -1/8. Divide by 4 on both sides and get -1/32. The value of p is important because it tells us where the focus is. Since this is a horizontal parabola, the focus is going to be on the x-axis. -1/32, 0, which is very, very close to the origin, essentially on, or just barely to the left of the origin. The directrix then is going to be across from that, across from the y-axis, and it's vertical, so it has the equation x equals 1/32. What we need to do now are find some other points on the parabola. There were a couple of ways discussed in class. One was to use the focal diameter. I believe for this particular problem, going back to something we may be a little more familiar with, which is making an xy table, it might be quicker to generate some extra points on this graph. So we can choose values of x, but keep in mind, once we choose values of x, we're going to have to square root them so we can get the value of y. So we need to be careful on the values of x that we choose. What I mean by that, if we let x equal -2, for example, we plug -2 in for x, that leaves us with the equation y squared equals 1/4, because -1/8 times -2 is +1/4. If we square root both sides, we're going to get plus or minus 1/2. So we're going to get 2 values from that. One's going to be +0.5. The other one's going to be -0.5. Another value of x that would be good to use is -8, because -1/8 times -8 is going to result in y squared equal to 1, and if you square root both sides, y is going to equal +1 and -1. So all the way out at -8, we have y is equal to 1 and -1, and when we let x equal -2, we were at 1/2, +1/2 and -1/2. Now you can see this is an extremely skinny parabola. Matter of fact, the closer the focus is to the origin, the skinnier, or to the vertex, the skinnier this parabola becomes. Okay, question 2. The equation of an ellipse with the foci and the vertices as stated. What we need to decide is what type. Now it's not asking us to graph this, but I'm going to take a look at a graph here. if the vertices are at positive 10 and negative 10, and the foci are positive 4 and negative 4, what we end up with is a horizontal ellipse. That's important because that determines the type of equation we're going to use to represent this ellipse. Because this equation, or because this ellipse is horizontal and it's centered around the origin, we're going to use the form x squared over, and I'm going to put the a squared underneath the x squared. A squared on an ellipse represents the larger value, or where the value from the vertices, and since this is a horizontal ellipse, that goes underneath the x variable. Then it's y squared over b squared. This is equal to 1. Now the vertices, plus or minus 10 tells us the value of a. If a equals plus or minus 10, then a squared is equal to 100. So that's the value that goes right here for a squared. Now to find b squared, we need to use the foci and the vertices, and remember the formula c squared equals a squared minus b squared. 100, well, c squared is going to be 16 equals 100 minus b squared. If you subtract 100 and manipulate this equation, you're going to get b squared is equal to 84. And we don't need to square root both sides because we're interested only what b squared equals. B squared is equal to 84, so that's the value that goes here. So our standard form equation of the ellipse is x squared over 100 plus y squared over 84 is equal to 1. Okay, I know this one is making a lot of students apprehensive because of the large numbers. I'm going to solve this one using some scientific notation to make the numbers, or at least writing the numbers, a lot more manageable. I think it would help to draw a diagram of what's happening here. Imagine the solar system on a two-dimensional graph. Okay, way out here we can let this little teeny point represent Earth. Okay, and the sun is actually not at the center of the orbit, so if this represents the sun, okay, the Earth travels around the sun in an elliptical orbit. Okay, now when the Earth is closest to the sun, that's called the perihelion. This is, according to our information, 147 million kilometers. So from here to here is 147 million kilometers. Okay, if the Earth revolves all the way around here to this point, that's called aphelion. That's when it's farthest away. So if the Earth were over here at this point, the distance from here to the sun, 153 million. Now, a distance that's not given here is how far away is the sun from the center. It's 3 million. Which means the distance from the Earth to the center of this elliptical orbit, okay, which are the vertices, is 150 million kilometers. Now, rather than writing all these numbers with so many zeros, let's switch to scientific notation. 150 million is 1.5 times 10 to the 8th kilometers. Now, what's being asked here is an equation of the Earth's orbit. So it's the equation of an ellipse, and the way we've diagrammed this is going to be a horizontal ellipse. So it's going to be x squared over a squared plus y squared over b squared is equal to 1. The vertices at 1.5 times 10 to the 8th, that equals a. So what we need to figure out is a squared. Now if you take 1.5 times 10 to the 8th, 1.5 times 10 to the 8th power, and square that, we're going to end up with 2.25 times 10 to the 16th. That's the value of a squared. So that's the value that's going to go underneath the x squared term here. What we need to find out now is the value of b squared, and it's like the problem above it, problem 2, we need to use the formula c squared is equal to a squared minus b squared. Now c is the location of the foci. The sun acts as is the location of one of the foci. Its distance from the center of this ellipse is 3 million. Okay, that's 3 times 10 to the 6. That's the value of c. So when we square that, so c equals 3 times 10 to the 6. When we square that, c squared is going to equal 9 times 10 to the 12th. So we have 9 times 10 to the 12th equals 2.25 times 10 to the 16th minus b squared. What we need to do now is to find, we need to get b squared all alone, which means we have to combine these two into one expression. Now we cannot subtract these two unless they are in terms of the same power of 10. This is 10 to the 12th. This is 10 to the 16th. What I'm going to do this in a different color, 2.25 times 10 to the 16th. If I move this decimal spot 4 to the right, that's going to take off 4 from the exponent. So if I do 22500, I can write that. And the reason I'm writing it this way is this is 10 to the 12th. This one over here is 10 to the 12th. Now I can subtract 9 times 10 to the 12th from 22,500 times 10 to the 12th. So if I have 22,500 times 10 to the 12th, and I subtract 9 times 10 to the 12th, that results in 22,491 times 10 to the 12th. And then if I move the decimal spots, the decimal 4 more to the left, and increase the exponent back to 16, this is going to be b squared is equal to 2.2491 times 10 to the 16th. So now we have the value of b squared. So our equation can be written as x squared over 2.25. I need some more room here. X squared over 2.25 times 10 to the 16th plus y squared over 2.2491 times 10 to the 16th is equal to 1. Okay. Question 4. A sheet of plywood. I can do better than that. Much better. I know it's cheating, but it's 4 feet by 8 feet, and a carpenter wants to make an elliptical tabletop. A few weeks ago in class I described a method that can be done, and it's called the thumbtack and string method. What happens is, if you imagine a graph superimposing here, so you find the center of the sheet of plywood and imagine an XY axis with this as the center, and the ellipse is going to be centered around that origin. What we need to figure out are where the tacks are going to be located, because the tacks are going to represent the foci of the ellipse. So we have the two foci, and you attach a length of string to the two foci on tacks. So we need to know the length of the string, how far apart the foci are, and that's what they're asking. What length of string should he use, and how far apart should the tacks be located? So now we know that he wants to use the most amount of board possible, so he's going to have the vertices of this ellipse be all the way at the end. Okay, that's the major axis. The minor axis is going to be located here and here. We need to figure out the length of string to be used. So let's first figure out how far apart the foci are, or how far the foci are from the center. The foci are found using the formula c squared equals a squared minus b squared. A is the total length of the horizontal length here is 8. So the location of the vertices is 4, 0, negative 4, 0. Up here is total length of 4, so it's 0, 2, 0, negative 2. So if the vertices are plus or minus 4, that means a squared equals 16. B squared is equal to 4, so c squared is equal to 12, which means that c is equal to plus or minus square root of 12. So from here to there, from the center to the focus, is the square root of 12. Same thing here, from here to there is the square root of 12. Now, we need to figure out the length of string to be used. The length of string, let's see, what he needs to be able to do is tie a string between the two tacks that's long enough that if you were to stretch it out, it would reach all the way up to the top of this. So if we imagine the string being pulled tight, it would have to go from here and back down to there when it was pulled tight. So if you can figure out this distance, it's going to be the same as that distance. Now we can figure out this distance from this focus here up to that point using Pythagorean Theorem. From here to here is the square root of 12. From here to here is 2. Okay, this is the square root of 12. So Pythagorean Theorem says a squared plus b squared equals c squared. A squared is 12. B squared is 4. 12 plus 4 is 16. Square root of 16 is 4. So that piece of the string has a length of 4, which means that this piece of the string also has a length of 4. So the length of string he needs to use to have an 8-foot string tied between the two foci. Now, how far apart are the foci? Well, it's the square root of 12 plus the square root of 12. Now, the square root of 12 is approximately 3.4. So if you have 3.4 added to 3.4, foci are located about 6.8 feet feet apart, 3.4 feet from the center. Okay, find the standard form of this conic. We're going to need to complete the square. So I'm going to subtract 26 from both sides. And then you have to complete the square on each separate variable, on each expression with each variable. So I'm going to complete the square on x and then complete the square separately on y. The x expression here has a leading coefficient of 2, so if I factor out the 2, then the term that completes the square, half of b, half of negative 6 is negative 3, and we square that, you get 9. Remember over here we had a negative 26. So 2 times 9 is 18, so we've added 18 to the left side of the equation, so we need to add 18 to that side. Now, with the y squared, we're going to have y squared plus 6y, and to complete the square there, we need another 9, which means we add 9 to that side. Now, if we take a look, x squared minus 6x plus 9, that factors into x minus 3 squared. And then y squared plus 6y plus 9 factors into y plus 3 squared. That's equal to 1. Now multiplying by 2 is the same as dividing by 1/2. So I'm going to change this to x minus 3 squared divided by 1/2 plus y plus 3 squared for 1 is equal to 1. This is an ellipse because both variables are being squared and it's plus sign between them, so this is an ellipse. We've got to determine what type. And you take a look at the denominators. 1 has a larger value and it's underneath the y variable, so that makes this a squared. A squared is equal to 1, which means that a is equal to plus or minus 1, and since it's underneath the y variable, it's going to be vertical vertices. So this is a vertical ellipse. B squared is equal to 1/2, which means that b is equal to plus or minus square root of 2 over 2. Square root of 2 is about 1.4, and if you cut that in half, you get about 0.7. So this is approximately plus or minus 0.7. And now we also need the location of the foci. C squared is equal to a squared minus b squared. A squared is 1, b squared is 1/2. 1/2 from 1 is 1/2, so c squared is equal to 1/2. Square root both sides, and you get c is equal to plus or minus, again, square root of 2 over 2, which is about 0.7. There's also a transformation occurring. X minus 3 moves the graph 3 units to the right. Y plus 3 moves the graph 3 units down. Okay. So, again, this isn't the best graph here to be looking at. Let's see. Because the numbers we're dealing with are very small. Let's see if I can generate a new graph here to make it a little bit easier to graph. Okay, this ought to work a little better. So if we shift the origin to the right 3 and down 3, and imagine this as our new origin. A squared, or the values of a plus or minus 1 are vertical, so from our new origin we're going to go up 1 and down 1. Okay. The values of b are plus or minus 0.7, so that's to the left nearly 1 whole unit, and to the right almost 1 whole unit. And the foci, plus or minus 0.7, those are vertical as well, so that's nearly 1 whole unit up. We have focus 1 and focus 2. Okay, this is a hyperbola. We need the standard form of the equation. The foci are on the x-axis, and the vertices are on the x-axis, which makes this a horizontal hyperbola. Since it's a horizontal hyperbola, the x squared is going to be written first, so it's x squared over a squared minus y squared over b squared is equal to 1. The vertices give us the value of a. A is plus or minus 4, which means a squared is equal to 16. To find b squared, we can use the location of the foci and the formula c squared equals a squared plus b squared. The foci plus or minus 5 means that c squared is equal to 25. A squared is 16. If you subtract 16 from 25, you get 9 is equal to b squared, which means that b is equal to plus or minus 3. Once you know the values of a and b, we're going to draw the central box. And this is, again, a horizontal hyperbola. So a goes on the x-axis, b goes on the y-axis. Then we draw our central box. From the central box, we can then use the corners of the central box to generate the asymptotes. Now the hyperbola fits in, goes through that vertex, and here we need a location of the foci and plus or minus 5. So one focus is there at positive 5, the other focus is there at negative 5. And that's part 1 of this review.